All right, so we're doing acids and bases ranking, and I have this worksheet here. Cool. So let's just rank these from weakest to strongest.
Perfect. Okay, so looking at the farmost structure, we have a benzene ring. So it's already leaning a little bit more basic. And we also have a negative charge on the O and a positive on the N,
Hmm.
but it's still double bonded. Okay. And then O, we have 1, 2, 3, 4. So two sets of lone pairs. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, I'm with you. So I would rank them. And then 1, 2, 3, 4 on that one. So I would almost rank them 4, 3, 1, 2.
Okay. 4, 3, 1, 2. Okay, so let's talk about it. You want to explain your reasoning before I kind
Yeah.
of divulge what I think?
So I'm kind of arguing that the benzene ring attached to the carbon would be like the most wait, hold on. I think I'm rethinking my thoughts.
Okay.
Because having a positive, yeah, no, I'm not rethinking my thoughts.
Okay.
The weakest. Wait. Okay, hold on. Now I've confused myself because if it's more acidic and 4 is the strongest, which means it's the least basic.
Hmm.
Yeah, no, I'm still okay with 4 because having that positive on the nitrogen means that it's electron deficient and it
Good.
could be attacked.
Good. Very good. Okay.
Then my argument for 3, I think I need to flip this around because I think 3 is actually going to be 1.
Okay.
Because wouldn't that be the best base out of all of them, given the 2 lone pairs in the oxygen and then the 3 double bonds?
Okay. So change that one from 3 to 1.
Yes.
Okay.
And then the oxygen kind of pulls this and makes that a little bit more like a partial negative, and that carbon maybe a little bit more partial positive.
Hmm.
So compared to the other one where it's all carbons and hydrogens, so I would maybe look at that as making that a better base to donate its electrons. So then I'd do that as 3, and then I would make the carbon attached to the benzene ring 2.
Okay. Sorry. So
Okay,
so this one, what number?
that would be 2, and then
Okay.
the one with the hydroxyl group would be 3.
This one will be 3.
Yes.
Okay.
Okay. Now I
All
feel
right.
better about this.
Okay, so let's do it together. So I'll start with the one you did on the left. I
Mhm.
thought that was really good. Your ability to find something that's deficient does make that the strongest acid. There's a few things going on here, and I think if I start to say one fact that you might start changing your answers again, but we'll see.
Mhm.
I don't know. So what there's a few things going on. One, you have three uh different rings that have benzenes, right? And this one
Mhm.
doesn't have a benzene. So when we think about acidity, remember that the more resonance you have, right, the more acidic it's going to be. So automatically then these three are going to be more acidic
Mhm.
than this one, right? Because this one doesn't have the strength of the delocalization ability when you compare its conjugate base and what these conjugate bases can do compared to this one, you know? Okay, so
Got
that's
it.
my first hint, right? So these three are going to be more strong acids than this one. It's going to be the worst acid, okay? So I'm going to put a 1 over here, but you did pretty good, right? This was a 4, and then
Mhm.
you were really close with the first ranking. And then when you changed it, it kind of changed all three
Yeah.
of these answers. But the first one you had actually had it was pretty close to getting them. Okay, so this one's going to be the worst acid. I'm going to talk about the delocalization of this compared to the other one in a second. And then between these two, um, so this benzene ring has an OH group, right? Versus this
Mm-hmm.
one has a methyl group. So when we rank the acidity, right, this one's going to be the next best acid. So I'll rank it as number 3, which is what you originally had,
Mm-hmm.
right? Um, and I'm going to rank it as number 3 because it's second place. Why? Why is it not better than the one on the left? Because if you compare these two now, what do they both have in common? They both have the ring. Okay, well, all 3 of these have the ring. So what separates all 3? Okay, well, these two both have OHs. Okay, so now I know to compare these two directly and see what they have different. This one has well, let's call it an electron withdrawing group because you're going to start to advance your vocab. And so just like you were able to recognize it as an electrophile, we're also going to call it an electron withdrawing group because that makes sense, right? The electrons are being withdrawn, and what does that mean? It means there's partial positives, and partial positives and full-on positive formal charges are a sign of electrophilicity. So that, like you were saying, this thing could be attacked. Something could come and attack it. That's why that's the best acid. This one doesn't have that, right? But it did have the same characteristic of the OH, so that's why this one is going to be better than this one.
Got it.
This one doesn't have as good of a conjugate base. If you think about a conjugate base, let's say I take something super basic like sodium hydroxide
Mm-hmm.
or a carbon that's negatively charged. You haven't seen that before, but let's show you some new things. You'll just be even more prepared down the road. So take something that's super basic. It's going to find the most acidic proton. That's going to be the most acidic proton compared to this H, and that could be a different type of problem too, right? You could have one drawing, and it could be asymmetrical, and say, oh, this is A, B, C, D, E, F. Which of the following is the most acidic hydrogen? This is the most acidic H because, of course, it's right next to the partial negative O. That's pulling on it. That's like kind of that induction effect. But then also, if you think about the conjugate base, now this is an O minus. Let's draw the O minus here, and let's watch how far that resonance can go. So if this is O minus, remember that our definition of acidity is how far can that resonance go? I can go here, and then I can go here, and then I can go over here, and then I can go, I don't know, let's end right there. That's a pretty far distance. You went all the way around the ring. So that's why these are better than this one, right?
Got it.
This one doesn't have
Okay.
an OH. It doesn't have something that's like obviously like, hey, come and hit me. Like, come
Mm-hmm.
take the H and I'll be negative and then have a conjugate and then we can do resonance, right? It's kind of like, oh, we don't really have that same scenario. We have it within the ring, right? But there's nothing off the ring that's kind of like screaming, hey, let me come to the ring and let's do all of this.
Got it.
And then same story for this one. When this becomes negative, what's it going to do? It's going to come here, then it's going to come down here. But then what's cool about this other group is that it can actually extend all the way now, like off the ring. You can go here and then push this to there. Look how far that resonance went. So again, another reason
Mm-hmm.
why with an electron withdrawing group or your ability to find electrophilicity, it's so good that you found that was a positive. I'm telling you, those little like tips and tricks, right? It's adding up and helping you on different problems. So that's why this is the best. This is second best. This is like third. It's still better than this one because this doesn't have that ability to pass any resonance to anywhere, right? It would be localized. Okay, cool. Did that help?
Yes. Yes, it did help a lot.
Cool, cool.
Because I was getting more caught up with the ring itself rather than the conjugate bases.
Yeah, good,
When it should be the other way around.
good. Gotcha, gotcha.
Okay.
Okay, cool.
Yes.
Let's do, because that one's similar. I usually will follow it up and do like, okay, let's do another one, but let's do, I actually have a different one too. It's funny because when I made this worksheet the first time, the key is different than the practice. So I like my key one better. Um, Let me see. Let me just take a screenshot of it and then I'll bring it in here instead of drawing it. Okay, so I'll just drop it in here one more time. Oh, Bluetooth is off. Let me turn the Bluetooth on. The iPad and the Mac are actually, I don't know if you know that function, but you can like take a screenshot on one device and then you can copy paste it on the other. Does that like
I
common?
just found that out
Oh, okay.
for my like OChem notes.
Cool, cool.
Um, the first time it actually did it automatically, and now it'll also do it like my phone, where like
Yeah,
it'll unlock all my devices at the same time and ask like which device it wants to be copied to. And I'm like,
yeah,
interesting.
that's pretty cool. So we kind of did this one down here, but let's do this one here now. So it's similar, but a little bit different. All right. And then we'll open up the other worksheet after this one.
Okay. Alrighty, so okay. We have a ring SO3H4NO2. We have a triple bond with a hydrogen. And we have okay. So I know that double bond. Okay, so the C. Okay, this is gonna be our weakest acid. It's gonna be just all sigma bonds
Mm-hmm.
because that can't really have resonance at
Yeah.
all.
Mm-hmm.
There's nothing to move.
Good.
Then you technically could move the double bond. Well, yeah, you could move like that down that way, and
Mm-hmm.
then that would give you a positive, and then that would give you a negative. And I guess you could do it on the other way as well. You could also, so for triple bonds for resonance, she was talking about in class how like we can move them, but we don't prefer to move them.
Mm-hmm.
And these ones you can really only move it one way because nothing else can really happen to the hydrogen. So then I would make the argument that the triple bond would be 2, and then the one would be 3, and then the benzene ring would be 4 because you can move it around quite a bit because of the lone pairs on the nitrogen.
Good. Yeah, so when you think about moving things over a greater distance, that's super helpful. Obviously, that's going to make this our number, our what we're
Hmm.
calling it for, but it's our best one, right? It's the strongest acid.
Yeah.
And then same thing here, there's nothing to move, so that's the weakest. Now between here, don't forget that other trend that you brought up earlier, right? If this is sp3, then this S character is only 25%, right?
Right,
If
and
this is
that's SP.
sp2, then that S character is
Got
going to
it.
be 33%. And then if this is sp, then that S character is going to be upwards now to 50%, right?
Got it.
So although you're comparing, there's multiple trends happening at once, but between these three, since this one's an outlier, then you can just use one trend, which is your S character, to compare and contrast the three groups here, right? Going
Got it.
from here to here to here is increasing S character. So that would have been your rationalization for having the number 2 be on the left and then your number 3 be on the right.
Got it. So then, as far as strategy, I have to remember if I'm ever in doubt between, like, for example, like delocalization, there wasn't like a super great answer to decide between 2 and 3, then find the common thing between 2 and 3
Yeah,
to
yeah.
then decide. Okay, got it.
Because for 2 and 3, that whole delocalization conversation's not as good, right?
Yeah.
Because with the other groups, like with the problem we did first up here, these make a lot of sense because there's an obvious hydrogen that can be deprotonated, and then you can pay attention to what that conjugate base looks like. Here,
Yeah.
the protons are a little bit less obvious to pay attention to. Um, and let me see, where's my drawing? Here. Um, so yeah, going back to your triple bonds, they tend to stay as triple bonds. The argument there is the triple bond is very reactive. Remember that pi bonds like to go out and do work, right? So the pi bonds want to be bases. So it's kind of interesting, right? Because it's like it's an acid, but you're saying it can act as a base. Um, so the acid, um that we're looking at, the triple bond is more acidic than a double, which is more acidic than a single, right? But when we talk about the conjugates, now, right, like if I see a triple bond that's negatively charged, that carbon on the very end is negative, it can go out and go do work. It can act as a base. It might not be a very good base compared to like, let's say you have a single bond carbon that is negatively charged. That's going to be a better base than the triple bond one
Hmm.
because the triple bond one is still carrying that increased S character trend, right? So that's kind of weighing down your basicity trend. So, triple bond that's negative is still not going to be that great of a base. It can act as a base, but remember it has the triple bond. So like triple bonds are relatively more acidic than a double and then compared to a single. So
Yes.
just kind of keep that in mind. And the reason I bring that up is because you probably won't have like negatively charged triple bonds that you're dealing with a lot in the class, but you will in like 2.5 weeks you will be doing cyanides, which are negatively charged and triple bond. And so then you have to think about like, oh, is that like really good? Like maybe not that
Hmm.
great. And then why? Because it has a triple next to it versus something else might be better, might be a stronger base. Well, why? Because it doesn't have a triple or a double next door. So now like you have more localization on that O minus. I'm telling you, all of this stuff is just preparing you, in my opinion, for SN2, SN1, E2, E1 reactions, which is arguably the hardest part of the class because
Hmm.
that's when you get to like the true OChem. Like what everyone thinks of as OChem, that's it,
Hmm.
right? Like it's
Got
there.
it.
So all these trends are helping
Okay.
us, like your ability to find a base or an acid. Cool. Awesome. Any questions with that one?
Nope.
Awesome. Super fun. Okay, let's do the other one. This one goes back to some BLA, BLB, and that kind of stuff. We can strictly keep it to more of like a Lewis conversation. I'm
Okay.
not as concerned about bringing up the BLAs and the BLBs. I mean, they'll be there, right? But let's try and focus on the LAs and the LBs.
Yeah. Okay. So just writing my notes. Nucleophile, electrophile is LA, and nucleophile is LB. Okay. Because if I don't write them down, I never get them straight in my head.
Yeah, yeah.
Okay, and then when talking about Lewis acids, we're talking about electrons strictly. So in Lewis acid, there's an electron deficiency. I can't spell that.
hmm
And then she likes the terms empty orbital,
Okay.
which is one and the same. And
hmm
then here we have electron donate, which generally means like a negative sign or a surplus.
hmm
Okay.
Cool. Okay, so we have four different structures. They're not compare and contrast, so they're kind of like four different problems, and we'll just go from the top left and work our way to the right. So
Okay.
basically trying to identify if it's a Lewis acid Lewis base, and then we move on to the next one.
Okay. So I know that the nitrogen has two H's attached, which means it's going to have one lone pair.
hmm
And that lone pair is going to tend to donate.
Good,
So I would argue it's a Lewis base slash nucleophile.
good, perfect. And I wouldn't argue that it is a Lewis acid, um, because I mean, you could have the H be taken if you found something that was more basic. So like it's kind of like up for debate, but
Hmm.
nitrogen itself is pretty basic. So I feel more confident with calling it just the Lewis base. Versus if you had something that was a little bit more neutral and that can kind of be like both sides, then you
Hmm.
could possibly call it a Lewis base or Lewis acid. We'll
Okay.
have a few more examples. We'll see possibly
Okay.
acting as both. But nitrogen's very
Oh,
basic. Think about that
yeah.
trend moving to the left on the row of the top right of the periodic table. Okay,
Yes.
cool. Next
Okay.
one.
So water is literally the bane of my existence because,
Oh, is this the one? Is this the one that the professor said to only count it
consider,
as one versus the other?
yeah, and the problem set, she counted it as acidic, and we all got it wrong. So,
What was it counted
um,
as? Was it both?
it was both. Because you could make an argument that the lone pairs on the oxygen will
Mhm.
donate, but
Yeah,
then you could
yeah.
also make an argument that the hydrogen's going to leave and leave you with an OH
Well,
minus.
and that's why it is both. I remember the first time I taught you about water, I said that it was amphoteric, right? And so it can act as both. So because if you think about like water plus acid, then there's no nucleophile to come by and take the H. So in that case, then the O is going to be acting as an Lb, right? It's going to donate
Mhm.
electrons, go grab the proton. But if you put water plus sodium hydroxide, then it's going to act the other way, right? So
Yeah.
H2O plus NaOH. Now your OH minus is going to act as the base. Your H2O is going to act as the acid. So then this can be a La as well as a BLA, BLB, etc. Right?
Yeah.
Um, okay, so in this case, we're going to do both. So H2O plus NaOH makes H2O plus NaOH. Kind of funny.
Right. Yeah.
Okay. Next one,
Okay.
CH3OH.
So the C, so then in this case, the H's are going to come off and the O is not double bonded. 1, 2, 3, 4. So it means it has two lone pairs.
Mm-hmm.
So I would still make the argument that it's a Lewis base.
Lewis base. Great.
Yes.
So because this O is less basic than the nitrogen, here our CH3OH is actually, because I'm going to give you a couple terms now and again. These terms are about 2 weeks out, but I'm going to be very specific when I start describing some of these terms like strong base, poor base, good nucleophile, poor nucleophile. We've really only learned up to this point nucleophile versus electrophile. But then within that, you can have different gradations of, well, what type of nucleophile is it? Is it a strong one or is it a poor one, right? What about our strong bases? Or what about our bases? Is it a strong base or a weak base? Like now I'm going to start throwing those terms in there. So CH3OH is a weak base. It is a poor nucleophile. Okay. That has like the wrong connotation, right? So poor nucleophile makes it sound absolutely horrible. Like it's not gonna be a nucleophile, but it still is a nucleophile. It's just not as strong of one as something like sodium hydroxide, for example. And the reason is because if you think about, remember the difference between ionic bond versus a covalent bond, this is a covalent bond. O bonded to H, O bonded to covalent, right? But with your sodium hydroxide, it's ionic, so that OH minus is it's negative, right? So you have a full-on formal charge there. So that's the difference between understanding like how do I know to categorize something as weak or poor versus strong and like, good. That's really your best differentiator. And I've always kind of said since day one, super paying attention to like negative signs and positive signs. That's the best way to kind of, and then I started throwing terms at you, right? Like negative signs you associate with nucleophilicity and basicity, right? Same thing here. But now we're just kind of breaking it up a little bit for like strong and weak. Um, okay, so since this is weak, the O can act as a nucleophile. So of course it's an LB. But if I put this again in the presence of sodium hydroxide, your OH minus can actually come by, snag that H, and delocalize, put all that negative charge on the O minus. So this can also act as an LA. So tomorrow, I think that it's going to be important for you to consider those things. So how I would approach these problems so that you don't get too muddled, because I feel like it's a muddling spot we're at. It's just kind of,
Mhm.
I think start with the extremes. There's going to be really obvious ones that are definitely acids and like don't overthink it, right? And then same thing, obvious ones that are definitely bases. And then try and work your way towards the middle where you're like, oh, here's water again, right? It tends to be the poor nucleophiles can go both ways.
Mhm.
The ones that are super strong base like OH minuses and stuff like that, only going to be LBs. No potential to be the BLAs or the LAs. And then the best thing, and this is going to sound silly, but the best way to find your acids is to look for things like H plus, H3O plus, H2SO4, H3PO4, right? HBr, HCN, those things, what they all have in common is a covalent bond between a hydrogen and something that's polar or electronegative. So it induces that difference in the polarity. So right there, like those alone, like finding something that's really, really basic and then finding all of those acid examples, that's going to be a bulk of them, right? So don't
Mm-hmm.
get too confused. It's really the poor nukes here in the middle that can kind of act as both. So
Got
it's
it.
like more of a, I would say like 10 to 12%, right? Not
Yeah.
like this is going to be half the test, you know? Okay,
Yes.
cool.
Yes.
Hopefully that helps though, because now you'll see it tomorrow and you'll like
Mm.
possibly consider. And then you can always make that judgment call. Just go one way or the other. But these ones can be both. So LB
Yeah.
and LA.
Because her
Cool.
favorite questions on these are like where it like which ones have the electrophilic carbon
Okay.
and
Yeah, yeah,
which
yeah.
ones will act as nucleophiles in every situation. Those are her two favorite questions about that type of stuff. So like nucleophile in every situation, you want a good nucleophile.
Uh-huh.
And then electrophilic carbon, you're gonna have the pole of a partial negative, a partial positive somewhere where that
Yeah.
carbon could technically accept something else.
Yeah. And that's a good point because again, here, for example, just because this N has that pool, right? Partial
Mm-hmm.
negative, partial, there's not really a good place for us to come in and attack here, right? Versus like
Mm-hmm.
over here, this one is much more obvious, right? You got a
Yeah.
partial positive here. You know that if you brought something here, you could break a pi bond and move in that direction. So like that's a good indicator in terms of what you were saying, the two questions that she likes, identifying that electrophilic carbon, for example, you know? Yeah, awesome. Okay. Uh, last one over here on the right, and then we'll go to the second column.
Okay, so we have two lone pairs in the oxygen, and then the hydrogen, which my first thought would be those lone pairs, I would look at it as an LB.
Mm-hmm.
Also, the conversation that we just had, that oxygen could get taken away and make the hydrogen could get taken away and make the oxygen fully negative.
Mm-hmm.
So then couldn't it also technically be an LA?
Yeah. So these here, for example, you don't need to know how they work, but these are very basic structures you're going to see in about 4 weeks. And they love to go grab that proton from this because you have that partial positive here. So because of that, this is a susceptible proton to be snagged. Granted, it leaves behind a conjugate base that's very localized. However, when you are in the presence of a strong base doesn't care about the havoc that it wreaks and leaves an
Mm-hmm.
aftermath afterwards, right? So if this is a stronger base, then it's going to come and take the proton. So for that reason, then this can act as a Lewis acid because you have a strong base donating electrons in this direction, which means that the definition of our La is accepting electrons. So this can most certainly act as an La. Yeah. And
Okay.
again, if you categorize this, this is another example of a poor nuke. It is another example of a weak base. Okay, cool. And then
Okay.
I'm going to put SB over here because these are examples of strong bases, right? So like those
Mm-hmm.
plus like an OH minus sodium hydroxide, something along those lines. Okay,
Okay.
cool.
All right, awesome.
All right, next column.
Uh, LiOH. So it's gonna be the Li connected to the O, connected to the H.
So think back to that first column on the periodic table. I know you probably have that periodic table just glued to the top of your computer screen, right? You probably like got a tattoo of it somewhere, right? I'm sure it's all over, right? But that first column of the periodic table, you have hydrogen on our first column. That's the
Hmm.
only one that's going to do the covalent bonds. And then the other
Yep.
ones like Na, potassium,
Oh, the spectator
lithium,
ions.
those are all spectators. Yep.
Got it. Okay.
So tomorrow, this is a
So,
good piece for tomorrow. Tomorrow, you want to make sure that you're looking out for spectators because that's going to be super helpful um for knowing whether it's a LA or LB. It's like it's game changer, right?
right, because then that makes the OH negative the
Yep.
Li positive,
Yep.
which obviously if it's negatively charged, it's a nucleophile.
Yeah, right. So the reason why it's a game changer is because if you can find the ones that are for sure negative like that, then you don't have to worry about like, is it both? Like you have an extreme in that case. And you can feel really confident with your extremes, and that's going to be a bulk of those questions. Cool. Yeah. So this is only LB.
Yes, I'm with you on
Yeah.
that. Okay.
So and then just because you see other metals, make sure you don't make the mistake to go too far and be like, oh, I see a metal. This must be, negative. It's that first column. So just be careful,
First
right?
column. Yeah.
Sodium, magnesium's 2+, but sodium, um, potassium, lithium, those are the main ones.
Got it.
Yeah.
Okay. Okay. Because then we have iron,
Mm-hmm.
which is a metal.
Exactly.
Yes.
Uh-huh.
But it's
Uh-huh.
not in the first column.
Exactly. Yep. Yep.
So then it'll be Fe to 3 COs.
Yeah.
And then this is one that has a lot of lone pairs because every Cl has 3 pairs.
Good.
And then for Fe, it being a metal, how many electrons does it want?
So a good question. With the metals, so like I'm just gonna categorize a few, right? Like Fe, aluminum, boron, not a metal, but boron. I'm grouping all these together. Boron, even phosphorus, okay? They all are a little bit more flexible in like the bonds that they can have. The iron's a little bit weird because it's not really matched up. I'd have to check the periodic table. If it is in the third periodic table, third column, then it makes a lot of sense. Um, but like boron, I know it's in the third column, so it likes to have 3 bonds. Um, phosphorus is in the fifth column, or sorry, in this, I think it's in the fifth column, so it likes to have 5. So most of the things they still add up to that column. Um, Let me just look at the iron real quick and see where it is.
Mhm.
Because if it is in the third column, then it makes a lot of sense. But if it's not, then you would just treat all of the metals the same. I'm on Amazon right now. $39 for a periodic table. Yeah, so I wouldn't worry too much about it. It's like technically in column 8, right? So you would just, if it's given to you like that and they don't give you a positive or a negative, just assume that it has all the appropriate bonds that it needs to have. Does that kind of make sense? Because they can throw a
Yes.
couple random metals at you, but you don't need to spend any efforts in there doing any of them. Okay?
Got it.
Yeah,
Okay.
just assume that it's appropriate number of bonds. So in this case, 3. Yeah.
Okay. So then this makes it pretty easy because with all those lone pairs, I'm still leaning towards a Lewis base.
Okay, so if you have the presence of so many Lewis bases, right? You want to
Mhm.
consider what they're doing to the iron. See that?
Oh, they're
Yeah, yeah,
making it a
yeah.
partial positive. Oh, right, because this is the same question that we had about aluminum, which means it can come get attacked.
Exactly. Aluminum.
So
That's
it's an
another good
acid.
example. Yep. And the aluminum
Got it.
actually
Okay.
happens to be in that third column. So for that
Hmm.
reason, the iron is acting super similarly to the aluminum. But it makes a lot of sense, the boron and the aluminum. Those are popular examples because these are more in the direction of one extreme again. So Lewis acid here. And the reason why I want to make you consider that it's an extreme because I don't want you to be like, well, this thing could be like a Lewis acid, but how about these? There's so many lone pairs here. I think maybe these can be LBs. So I'm going to make this LA and LB, right? This would be an extreme only towards LA because the halogens are inducing. The only thing that you can do here is to be the partial positive because you've created such a good electrophile. So this whole thing we'll consider an electrophile, you know?
Got it.
Yeah,
Okay.
yeah.
That makes
And then
sense.
also last thing with the halogens, remember that halogens are super picky and they only want to be we've done a few examples with halogens, but they tend to be and think of your naming stuff and how they look on an alkane. They're pretty isolated, right? They're kind of
Yeah.
doing their thing. It's not like they're bonded to like carbons on the other side of it too, or it's like attached to an oxygen or like a hydrogen. It's like no, you just have the fluoride the fluorine, it's attached to like all of the carbons, but that's it, right? And it has all of its lone pairs and it's pretty happy. And if it's not doing that, it's negative and it's on its own, right? It's super stingy because they're electronegative, you know? So that's why I don't want you to also consider it an LB, because it's not like this chloride is going to be like, yeah, you know what? Like I'm gonna donate today. I'm gonna go ahead and give, I'm gonna go be a LB and I don't know, go grab a proton. It's not going to want to do that, right? Because it wants to keep these electrons to itself, so it's not going to initiate that attack.
Got
Cool.
it.
Cool, cool, cool. Awesome. Okay, next one. Questions about that last one or no?
No, that
Okay.
makes a lot of sense. Okay,
Cool.
H3 plus. Well, a plus, I'm leaning towards Lewis acid. It's
Awesome.
deficient
Good.
in something in
Yep.
electrons.
Good. And I like that confidence because when you do see those positives, you can feel really confident that it's going to be on the acidic side, right? And when you see those negatives, you can feel confident that's on the basic side. Awesome. Yep. Yeah. This can't act as an LB. Yeah. Perfect. Good. LA only. Okay.
Hmm.
Next one.
Okay, and then this one we did say it had we kind of already talked about it a little bit. So it having an electrophilic carbon
Mm-hmm.
um would kind of have to make it La.
Yeah.
Um,
Yep.
but then follow-up questions one, two, three, four, five, six. Couldn't it also technically get delocalized?
Yes. Tell me what you mean. Tell me, because you're on the right track.
Well, because if it has, because let me just make sure that I'm right. Yeah. So oxygen wants six.
Mm-hmm.
So it has a double bond and two lone pairs. Couldn't you technically
You're on the right track.
pu-
Yep. Go with
push
it.
one of
Go
the
with it.
lone pairs down and push the double bond?
You're close. You're close.
I mean,
What
push the lone pair or push the double bond up, make it
push it
negative,
up,
then make it
make it
positive.
negative?
Yes.
Yes,
Yes, yes,
push
yes.
it up, make it negative, and then what can that negative do?
Well, it can donate its electrons then.
Sure.
So
Yeah.
making
So
it a Lewis base.
exactly. So this one can also be an LB because the carbonyl up on top can go grab a proton, and that's your ketone and aldehyde reactions in 118B. So
Got
this
it.
can go here and help kind of get the ball rolling, right? Now you have like a partial, a full-on positive up there, right? It just used to be like a partial negative, and
Mhm.
then this was a partial positive. So it's like, oh, I like kind of have an electrophile there, like that's great, like pretty happy about that. But then when you make the full-on positive here, then because of resonance, look what happens. Your full-on positive moves to your carbon. So now if you were to evaluate and say, hey, okay, here's a ranking question between these two, which ones do you think is the better acid or the best
Mhm.
electrophile? This, and this too, because remember they're the same when they're resonance. These are better than this one in terms of acidity and electrophilicity because this was only partial positive. But now, not only do you kind of have this double here, still inducing that partial positive, but you have a full positive, right? So that's a formal charge of positive
Mhm.
one. That's an awesome electrophile. Now we can, and that's actually the first step to these reactions. Your carbonyl up on top grabs a proton. And the reason is because that's an LB. Here's an acid, right? So that's an La over here. And then now you've made a better electrophile, and now you can take a nucleophile like a poor one. Hey, because what if a poor nuke isn't good at attacking? Well, that makes sense because it's poor. Okay, so if you can understand the really, really strong ones, then you know the other ones are probably not as strong, right? Which means they're poor. And if they're poor, maybe they can't attack as well, right? But if your LB up on top, grabbed a proton, made this thing a better electrophile, now your poor ones can attack. And that's the
Got it.
difference between memorizing reactions in 3, 4 weeks and like actually just things are clicking. You're like, oh yeah, that makes sense. I'm looking for like if you're kind of on the hunt for LBs and LAs, and like also using terms like electrophile and nucleophile, it's a game changer. You're like all of a sudden
Mhm.
looking at OChem completely different because you don't have to memorize anything. You just I could throw something in front of you and just be like, hey, analyze it. And you'd be like, okay, well, this is this and that is that and this is this, and then all of a sudden you're like figuring out the problem, right? It's like you don't have to memorize that.
Right.
Cool,
No,
cool.
absolutely.
Yeah. So that's why this is also an LB. It's a good point. Finding
Hmm.
the carbonyl up on top. Perfect. Cool. Okay.
Awesome.
Last row. Last row.
All right. Well,
Home stretch.
we have a halogen
Hmm.
connected to a hydrogen. 1, 2, 3, 4, 5, 6. So in this case, wouldn't they be happy if the hydrogen went away?
Uh-huh.
So wouldn't this not be considered a Lewis acid? It's not deficient in anything.
Okay. Okay.
Let me hold on. Because this kind of reminds me more of like Bronsted than anything with that hydrogen. Because I'm leaning more towards it being an acid because it would more likely donate that hydrogen because being a halogen, it's pretty electronegative. So
Hmm.
it'd be more concerned with keeping its electrons rather than
Okay. Okay.
accepting
Okay.
anything else.
So I heard I like kind of quoted you. So I heard the word acid, and then I heard here keeping electron for itself. Okay. Now between those two ideas,
Yeah.
what are you thinking leaning towards, like one or the other?
I would be leaning more towards it giving up its hydrogen.
Okay. What is that called with Bronsted? Giving up an hydrogen.
Oh my God. Hold on.
I know, right?
My brain's like turning off. So if it gives it up, it's a proton donor, meaning it's a Bronsted acid.
Awesome. Good. That can be so hard to turn that on. And the reason is because for me, I don't have that memorized. I have to kind of go back to Lewis for a second, think about what would Lewis do, and based on what Lewis does, then I could be like, "Oh, okay, well that makes sense. The proton did this, or this is what happened to the proton." So then now, oh, it must be a Bronson-Lowry acid because the proton was lost because a Lewis base
Hmm.
came by and attacked it. So it has to be Bronson-Lowry acid, a proton donor. Oh, so I almost work backwards.
Got it.
But that's why I've always taught like the Lewis is really, really, really helpful, right? Because
Hmm.
I think, and the class is driven on electron flow. The electrons move from an area that's more rich to an area that's less. So you should learn these definitions as the Lewis, and then the Bronson then is just kind of like, well, just look at the H. What did the H do? And then and
Yeah.
then you just match it up. Okay, so what's your final answer then? If it's BLA,
BLA. And then technically, so if it's BLA, then I would be leaning towards it like being an LA in that case, but there really isn't any deficiency for it to occupy because there's not a ton of electron movement. Like once that hydrogen breaks off,
yeah.
the Br becomes fully negative. One, two,
Let's
right?
pretend it's your lecture quiz and you just had to do 46 questions in 20 minutes and you have 14 seconds left. Did
I'm
did
just
the,
saying it's BLA.
did the stress Well, remember, but BLA is not on your test, right? It's either LA or LB.
Oh, well then I would go.
And now Dr. Levens is saying, okay, time's up. Everybody turn in their
No,
test. What are you gonna put?
I would say
And the TA just came up
a
to you to
Lewis
ask for
acid.
the TA just came up to you to
Yeah,
ask for your Scantron.
I would
Perfect.
say it's Lewis acid.
Good.
Yeah.
I try to create a stressful situation there. I'm stressed just thinking about that. Um, if you can identify that's a BLA, remember BLA has the word acid in it, right? So that's a huge hint for you. It can't be a base then, right?
Yeah,
That's a cheat way of cutting the definitions in half, right? If you can
yeah,
recognize that it's a Lewis acid, then it for sure can't be a Lewis base. It can't be a Bronson-Lowry
right.
base. Unless it goes both ways and then you have all four terms. But yeah, if you were able to say that it's a BLA, then it has to be LA for your answer. And you stuck to your guns, right? Like it was a stressful situation and you're like, I gotta choose, and you did it right. So for me, how I analyze this, the BR is pooling, right? The BR has the partial negative character. So remember, there is an area of deficiency here, right? Our H wants to be attacked. So, like you were saying, yeah, the BR is not gonna like do anything, right? It's not gonna go attack and it's not gonna be attacked, but it is inducing this H to be attacked. So this whole group is actually considered an electrophile. This is considered the most electrophilic atom, and it's going to be attacked. And when it does, we can apply both those terms. One, Lewis acid, because it was attacked, so it accepted electrons. And two, if it's being attacked by someone, let's say like an O minus, then that O minus is taking the H. So now your definition for BLA, bronzolaric acid, is a proton donor. Okay, that makes sense, right? It gave up the H in exchange for accepting electrons. Done.
Yes.
Cool.
Okay.
So
Alright.
this one, you were like kind of borderline considering,
Yeah.
right? But actually try to group this as one of those extremes. So
Okay.
the extremes would be like hydrogen with something that's electronegative. That's super, super good for identifying that it's probably going to be an acid, like an La. So a couple examples, like all of your fluorides, so like HF, HBr, HCl, HI, all just acids only. So no consideration for base. Um, H2SO4, I've tried to make that a big deal. That's an important one for this whole class and for 118B. So if you want to start getting comfortable with that, that's your sulfuric acid, H2SO4, very, very important. Remember that because they could give you this. Technically, you've had your first couple weeks in the books, so they could technically give you this, and you're supposed to know what its Lewis structure looks like. So I'll give it to you here. You have your H2SO4. But same idea. You have a hydrogen that's being next to a positive, or sorry, the O minus, right? So the same thing. This is pulling this way, partial positive, and so you can move this over here. Okay. Um, and then the reason why this is also a really, really good acid, if you think about the delocalization that can happen, if this is O minus, this can come down, which means this can go up, right? And if
Mm-hmm.
that goes up and this is negative, this can come down, and then this can go up. So that's pretty cool, right? That's a lot of resonance.
Mm-hmm.
Okay. So just
Okay.
trying to help you with some extremes so that you feel like you see one and you're like, okay,
Okay.
yeah, good,
Awesome.
good.
So CH, is this when it's triple bonded to N?
Mm-hmm.
One, two, three.
And then lone pairs?
8, 6, 5. There's one lone pair of nitrogen.
Good.
Um, okay. So I see two things here. I see the lone pair on the nitrogen as an indicator of it could possibly donate.
Mm-hmm.
Because it would be pulling that way. So then this, but then I also see the hydrogen with, but I don't see any resonance. So no, I'm sticking with my Lewis base.
Okay. So this one is Lewis acid. First
What?
one you got wrong, but hey, it's okay because this was 12 questions. So far you're on pace to get like 11 out of 12 right, which is pretty good. Um, this one treated just like it's an HBr, right? Or like an
Because it's
H2SO4.
so electronegative that it creates an area of deficiency.
Exactly. So your area of
Got it.
deficiency is here. And remember what we said about the nitrogen. So we were talking about a triple bond earlier, and we're like, okay, if it's negative, which this isn't negative, by the way, so it's not really even that good at being able to be a base. Um,
Mhm.
and it's next to a triple bond, which also makes that basicity go down again. You have like multiple
Right.
things now kind of going against you to say like probably base, probably LB, you know, so those things. And then also you want to consider the conjugate. So in this case, if this H is taken, the conjugate would look like this. And so then that there's a negative on the carbon, it's like, ooh, maybe that's not very good. But you can, oh, actually, let's see. Um, there might be resonance here, but it's not very strong, or I don't, if anything, I don't think it's helping our cause.
Mhm.
But with a little bit of resonance next door, that also helps our definition of acidity because again,
Acidity.
you're spreading out the charge over a greater distance. So you kind of have this thing going on. Um, this though, not as common as this. So if you had to choose and you were like stuck, stick with this, super popular. And then this, like let's say this was out of context. If you only had this, then you're if you were between these two, the carbon with the negative is going to be the base. So again, another reason to say this side's not going to act as an LB, right? This H can be taken, so it's an La. The conjugate base can act as an LB, but that's obviously not how you go through these problems. You don't look at the
Right.
conjugate and then say, hey, that's a LB, so then this answer should be LB too, you know? Um, but I drew this so that you could see this doesn't act as a base, right? This one would. So this one's La only. Okay, cool. Pretty good, pretty good, pretty good. All right, last two.
Okay. So we have a halogen and we have sulfur. Oh boy. So how would this look? Well, sulfur wants 6. 1, 2, 3, 4, 5, 6. 1, 2. So then could I 2 double bond and then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So far I have oxygen, 2 CLs coming off the oxygen with 3 lone pairs. And then
Mm-hmm.
a double bond to sulfur with 2 lone pairs.
Okay, pretty good, pretty good. I'll keep that. 2 lone pairs. Okay.
Okay. So, since sulfur, I know 1, 2, 3, 4, 5, 6. Okay, so the first thing that I see is resonance coming from the O to the S. So I could push that bond up, make it negative, make it positive. It's not a
Mm-hmm.
great resonance structure.
Mm-hmm.
Um, so that makes me lean a little bit more towards acids.
Pretty good. Okay, I like that so far.
Also considering that like CLs are a little bit more electronegative than Os, you can kind of see that they're pulling a little bit
Mm-hmm.
to kind of make that oxygen again a little bit partial positive.
Mm-hmm.
Um, so I would be leaning towards a Lewis acid
Lewis acid. Okay, good. So the SOCl2, the sulfur is gonna go in
in
the
the middle.
middle. Mm-hmm.
Okay.
It's gonna look like this. The reason why I bring this one up because if I were to list like 3 to 5, your SOCl2, PBr3, KCN, methanol, ethanol, and like H2SO4, those are very common reagents you're gonna see throughout your SN2, E2, SN1, E1, and then also alcohols and ether reactions. So that's why I'm showing you these ones, right? There's obviously like probably a million examples of like Lewis acids and bases, but I try to choose the ones that are like, okay, it's going to come back up again. So you might as well know what the structure looks like. Um, sulfur for sure can get hit, right? Because it's being pulled on like this. So yeah, definitely Lewis acid. Same thing though, like what we said about the carbonyl, right? The carbonyl with the double bond O up on top can go grab a proton, right? So
Right.
we'll also put LB for this.
Got it.
If you have notes from your professor, after today, it would be good just to go look and like now that you kind of have a more of an expert eye of like, hey, these are kind of like the tricky ones where it was like kind of both. Go cross-reference the professor's notes now. The reason is because you want to see like, oh, okay, like I've done this example and I'm seeing like it's both. If you can see anywhere in the professor's notes and like there's an example of a double like that, then it's gonna make you feel even better, right? But if you get to one, like let's say it's SOCl2 and she only writes Lewis acid, then now it's like, like because the relative Lewis acid here is much better than the Lewis base. You know what I'm saying? So
Right.
in
Right.
some ways, like it can act as both, but really like the LA is much stronger here than the LB would be, you know?
Got it.
So it kind of just depends. And it seems like, for example, with the H2O, that was already kind of like on both sides, and then it resulted in possibly some lost points, you know? So
Right. Right, right, right.
um I would just triple check and go look at some notes from the professor and see if you can find any examples and compare them to these
Okay.
ones, you know?
So whenever I see like a double bonded O, I should kind of have in the back of my mind that could probably go and grab a proton.
Yeah, yeah. And that's a great mentality to have anyways, because a whole chapter, let's say, is on ketones. The first step
Hmm.
is for this to go attack here. If you had an aldehyde, the first step is to go attack here. And then same thing with your carboxylic acids and esters and anhydrides and acyl chlorides. All of these, the first step in all of the mechanisms is actually to do that. So that's why I'm still sticking by that idea of like, yes, every time you see a double bond O, it can technically be a little bit of LB because the O up on top has that characteristic of being able to go grab a proton.
Got it. Okay.
And then acyl chloride here. And even when you get to, so like I know you're not going to do 118C, but even if you get to 118C, like these ideas are still super relevant for these
Hmm.
reactions. Like because you would have to rank these, and it's a fair question to ask now because you're doing acid stuff. But like if you had to rank these, you'd have to consider like this one, for example, is going to be a better acid than a ketone or an aldehyde. Why? Well, because there's double O's next door, right? Like this one has an O pooling here versus these ones don't have that extra O, right? So like these ones for sure, ketones and aldehydes, if you go look at their pKa's, they're not going to be as acidic as a carboxylic acid. Okay. But then between here and here, right, this one's a halogen versus this one's an OH. So again, the halogen's going to win. This is the best electrophile right here. That's all like
Hmm.
a 118C conversation, but it's relevant where you are now because you're comparing acids, you know? So
Right. Right, right,
kind of cool, right? And I see why 118A exists and like what you do in 118A.
right.
I mean, it makes sense, right? Because then it's a now you would just do all of this, and that's like that's a whole midterm itself, you know?
Right.
Yeah.
Right.
Okay, cool.
Okay.
Awesome. All right, I'm glad we reviewed that because we hadn't
Yes.
reviewed the Lewis stuff in a minute, but you're pretty good at it. So, for tomorrow, I would just because you are pretty good at it, just go with your gut feeling for sure. Like double check it, but if you're doubting yourself, I think what I saw was when you switched it, it tended to you tend to switch things to the wrong things. That's always hard,
Hmm.
right? But
Yeah.
it seemed like your original gut feeling was the right thing throughout our whole session tonight. So just
Okay.
FYI. Yeah, that's what it felt like.
Okay. Sick.
Okay. Couple naming and then call it a night. Do you want to do that?
Yeah, that works.
Okay.
Question about
Yeah,
PBR3
sure, sure.
is the only one that we
Oh,
didn't
yeah, yeah. Sorry.
do.
I got
No,
lost
it's
in there.
totally okay. Because I know that phosphorus actually has a lone pair on it
Yeah,
because it wants five.
yeah.
So going back to our original conversation about the halogens all pulling and creating an area of deficit,
Yeah.
does that still apply if you technically have an electron that it could donate?
This one, because of the three BRs pulling, only LA. Yeah,
Okay,
yeah.
got it.
And just mechanistically, if I think of different reactions, the phosphorus doesn't have enough nucleophilicity strength. Remember, compare your basicity trend, right? Like between oxygen and the phosphorus, oxygen is going to be a little bit better at going out and attacking things, right?
Hmm.
Um, versus phosphorus, not as much. And in this class, we don't do as much with phosphorus anyway, so it just goes to show that oxygen's a little bit more adept at being able to go grab protons, for example. Thinking back to
Got it.
protons is always a great thing because you don't need to memorize all of these things that could be attacked, right? So you just have to have one example and like an H plus or an H3O plus or water, like those are super good, easy examples to kind of like get your brain thinking of like, oh, could this thing act as a Lewis acid or a Lewis base? You know, like
Yes.
you don't need to memorize anything else right now, right? Cool. So yeah, in this case, because the BRs are pulling like times three, phosphorus there is just going to be attacked. And that's how the mechanisms work too. This is a alcohol reaction, so it'll be the last couple weeks in the course.
Okay. All right. Naming, and then I get to go to sleep.
Yeah, cool.
1, 2, 3, 4.
Yeah,
We
this
are
one,
at
this one's too easy. This one's
nuts.
too easy. So let's just do maybe like these three because you showed me you can do something like this.
Okay.
Just to be more streamlined because you have demonstrated to me that you can do naming decently
Okay.
well. So I think let's just do three instead of
So
all six.
perfect. Methyl.
Yeah,
Methyl. Methyl. Starting left to right. 1,
good.
2, 3, 4, 5, 6, 7, 8, 9. So we're at 2, 2, 6 trimethylnonene.
Perfect. Easy. I'm not even gonna rewrite it because you got it. Awesome.
Perfect.
Yeah.
Okay. Fluorine methyl.
Mm-hmm.
They're both in the middle, so it doesn't really matter what way I count. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. Yeah, they're both at 5. Okay, so fluoro and methyl. So methyl comes first. 5.
Mm-hmm.
Fluoro dash 5. Dash methyl nonene.
Perfect. Good.
And the last one. Uh we're gonna start counting from the right. So 1, 2, 3, 4.
Mm-hmm.
It'll be 1, 1 dibromo dash 3 dash methyl methyl ethyl propyl butane.
Mm-hmm. Where's the ethyl?
Oh, that was just me counting. So it's 1, 1 dibromo 3 methyl butane.
Oh, okay, perfect. Good, good, good. Sorry, I heard ethyl. Yeah.
Yeah, when sometimes when I count like methane, ethyl just sounds better to me than
Oh, I see. Got
methane.
you. Got
So
you.
I'll count like that way.
No, that makes sense. I have one more. I wrote it down.
Mhm.
So let me draw it. Okay. Let's do here, 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 here. Oh, that's dramatic. Here, here,
1,
here.
2, 3, 4, 5. Here, 2,
Can you
3.
believe that I took OChem in the era where I didn't have an iPad. Like iPads still weren't that big
Uh,
yet. Like it's not like
yeah.
all my friends had iPads and I was the only one who didn't. Like I was just on the cusp of like I didn't have one, right? Nobody
Mhm.
else really did. And then the next year after OChem, I got an iPad. Most of my friends didn't have an iPad. This was after OChem and I started tutoring and I was like, this is awesome. Now,
Oh
right,
yeah.
because you have an iPad, could you even imagine doing OChem without an iPad?
Like no. And I
Could you
know that sounds like so like I don't want to say privileged, but kind of because I have friends that don't have iPads and I'm like,
yeah.
how are you doing this?
Can you imagine only doing your OChem on paper and pencil? Like I had notebooks,
Yeah.
like this the colored spiral ones.
Well, because when so you were doing it in 2017, 2016.
2016 is when I took it. Yeah.
So I was a freshman in high school.
Did you did you have an iPad then?
No, I
Okay,
had a
okay.
spiral notebook when I was doing like
When did you get an iPad to start learning?
just this year.
Oh, okay. Okay.
Yeah.
That's
So
fair.
I did Gen Chem on paper.
Yeah, I did Gen Chem on paper too. I don't
But
re
Gen Chem was like equations. So it's basically like doing math.
It felt like you needed a pen and paper for that one
Yeah.
and like a what do they call those things? A calculator. Okay, let's do this one. Let's
Wow.
do this one.
Okay, so we got methyl, methyl. We got 1, 2, 3, which is a propyl. So then we're left with 2, 3 dimethyl dash 3 dash propyl. There's not a fancy name for it. No, because there's not a branch. Propyl and then hexane.
Wrong.
What?
I
No,
know. That's why I gave you this one.
I'm
Reevaluate.
not.
Where did you start from? Where did you start
Um,
from? Here or
oh, nuts. Is it? methyl ethyl. No, there's a
Which side did you start
yes.
from? Over
I
here?
started from the left. Yes.
Okay, and then where'd you go?
I went.
Up or down?
Oh, I went up.
Okay. Well, it'd be
Ah,
the
nuts
same.
is
It'd be the same,
yeah.
right?
Yeah,
Okay,
yeah.
okay. So, because again,
Uh,
this is not correct, but can you try and
yep.
figure out why not? So you had one, two, three, four, five, six. Okay. So try and
Hmm.
figure out why that's not right, because that seems like a good route. And again, that's the reason why I chose this. Why do
Interesting.
you think that's not a good route?
I actually don't know.
Good.
Oh, no, I don't know.
So remember the first step is always, right? It's good to like, okay, you kind of start you can kind of start wherever, right? And then kind of work your way
Hmm.
in. But you generally tend to want to start towards maybe the side that has like a bunch of stuff going on, right? So like I would have
Right.
started here too, and like it just makes the most sense. So like, oh yeah, let's like keep the smaller number. But remember, before you do that, you have to have the longest carbon chain first. That is rule number one,
Hmm.
right? So if I go here, yeah, this is going to be a small number because that's only going to be a two, and then like this will be a three, maybe like a three propyl and like a three, two, three dimethyl, but that's only going to get us to a carbon chain of one, two, three, four, five, six, or one, two, three, four, five, six. Watch what happens when I start here.
You
One,
loop.
two, three,
Um,
4, 5, 6, 7. Do you see
I didn't
that?
even know that was an option.
I know, right? So, because our brains are really good at identifying the central brand, and then our brain treats all of these as substituents, right? So you
Got
have to
it.
make sure you consider a substituent as possibly a main long chain, and this is actually the longest route. And that remember that's the first rule for naming, right? Even though this will be like a much bigger number here and here, that doesn't matter, right? Because the first step is always the longest chain.
Got it. So then the ones that I sent you where I was like, why is this different than the answer
Yes,
key?
and
It's because they were no, that's
sorry I didn't
okay.
get to see those. Yeah.
No, that's okay because they were kept. Oh, see, I didn't even know that was an option. Okay,
Yeah.
so
Yeah.
then it does become a methyl ethyl.
Probably.
One
I'd have to do it. So
methyl
you do one, two, three,
ethyl.
4,
Hmm.
5, 6, 7.
So
Oh,
then it
yeah, yeah,
would,
yeah.
right. So then it would be like 4 dash. When you have a methyl and a methyl ethyl, does the methyl come first?
The base name will be the alphabetical. That makes sense? So like methyl
Yes.
ethyl, the E would come before like this methyl, for example. So
Got
if you're gonna do methyl ethyl here, then at the 4 spot, the ethyl would technically come in the front. So you have like at the 4, you have 1, 2.
hmm
So at the 1 spot, you have a methyl, and then you have ethyl,
got it.
and
Okay.
then you have 4 methyl.
That makes
Yeah,
sense. Okay.
good. And
Mm,
then this one is 7. That'd
and
be
then it'd be
heptane.
heptane.
Yeah. If you
Okay.
wanted to, this could be a 4-methyl, and then you could call this isopropyl.
Right.
Sometimes that'll actually be better for you. Remember that the dies, tries, the terts, the sex, those don't count for the substituent when you're naming it alphabetically. But
Hmm.
iso is not a like ditri tetra, right?
Right.
Iso is actually part of the full name of isopropyl. So you would still count the I alphabetically. So you
Okay.
could do 4 dash isopropyl just to
Hmm.
like because sometimes you don't want to get caught in the weeds of like 4 dash parentheses 1 dash, oh gosh, methyl ethyl, which one comes first? Like that can be a lot. So in this case, a good answer would be like 4 dash isopropyl dash 4 dash methyl heptane.
Got it. Okay.
Yeah. But that's a super good one because then it reminds you to triple check your length of the carbon chain. You don't want to You don't want to assume that everything are substituents, right? Like look at that substituent and see, can that get you a longest route? You know?
Yes.
Cool. Oh, that was fun.
Okay.
That was a lot of good work. That was pretty
Okay,
good.
so so this weekend,
Yeah.